All right, everybody, I think we'll go ahead and get started. It's great to see a number of you online, and it's been a long time since we've had one of these webinars, since really near the beginning of COVID. So just a note, I wanted to let everyone know that this presentation is being recorded. So just keep that in mind. And today for this Above Science Cloud webinar, we have three talks lined up, one by Dr. Christoph Keller, who's going to talk a little bit about his use of machine learning on ADAPT, which is the larger kind of NCCS system where Above Science Cloud sits within. And then Matt Stroud is going to demonstrate some of the capabilities of the GPU cluster that are now on ADAPT. And then Dr. Paul Montesano is going to talk a little bit about the gridded Elvis data that he and the Vegetation Structure Working Group have put together and that is now located on ADAPT. And I will stop sharing my screen and we will let Dr. Keller take it away with his screen.
All right, thanks. So I'll move the ball over.
Yep.
Let's see. Okay.
So while he goes ahead and gets set up, I thought I'd just give a little introduction to Dr. Keller. So he's not part of our Above Science team, but he's done a lot of work on ADAPT using the machine learning capabilities there. He received his PhD in 2012 in atmospheric and climate science in Zurich, and he's been at Goddard in the GMAO office since 2016. So I'm actually really excited to see this research because I don't know as much about this either. So I look forward to hearing your talk. Thanks a lot.
Cool. Can you see my screen? Let's
Yep,
see.
we can see it.
Okay, great. Somehow I tried to minimize this. Okay, I hope you cannot see. Let me.
We don't see the WebEx bar
All
at
right,
all.
perfect.
Yeah, that's
All
fine.
right, cool. All right. Well, so thanks for having me. I guess I don't have to really give a lot of an introduction anymore. As said, I am at 6101, the Global Modeling and Assimilation Office, and I really work on atmospheric chemistry simulation. Think about it as air pollution, so simulating air pollution using satellites and models. And what I'm going to present today is, I think I have like 10 slides or so, it should be pretty quick, is a project that I did with my colleague, Matt Evans from the University of York, where we try to use machine learning to really accelerate the simulation of atmospheric chemistry. And kind of like the really big picture that I wanted to sort of like start with is that we can now, and this is a very recent development, that we can actually simulate atmospheric composition really at the resolution and at the level of detail that we have never been able to do before. So what you see here is in the middle, this is a computer simulation of atmospheric chemistry at 12 by 12 kilometer horizontal resolution. And just to give you context, when I started maybe 10 years ago or so, my PhD, we were dealing with 500 by 500 kilometer or so global simulations and thought that we were really cool. And now we get sort of like to the kilometer scale at the global level. What you're seeing here is this is one pollutant, this is nitrogen dioxide. And you can see sort of like the ship tracks that we can now resolve. You can see almost individual sources out now that it's over Antarctica. You actually see these are research stations. They use generators to produce electricity, and that's actually captured now in the model. So it's really cool that we can finally kind of like get to those resolutions. Of course, we also then integrate satellite observations to kind of like really figure out where are the sources, what is happening. And that gives us information about things like what is the air quality on the ground, what is the impact on human health, but also on like vegetation and crops, etc. And of course, things like wildfires, how do they spread, all that stuff. So it's a very exciting time actually to be in the field. We also have a ton of new satellites that are coming online in the next 5 years. So this is all really exciting. The problem with it is, first of all, we still need the models to fill a lot of the gaps in the observations. What I'm showing here, this is on the left side. These are some surface observations that we have for ozone, which is my favorite pollutant, as I always call it. And you see that we really don't have a great coverage of surface observations. And then on the right-hand side, this is satellite data where we have much better coverage. But especially with the satellites that we have now, we have only a daily overpass, and the chemicals, you saw that before, they change very rapidly. So just a daily snapshot might not be enough. And of course, we have things like clouds and then also the sensitivity at the surface. So ultimately, we do need the models to kind of like integrate all of the pieces of information that we have. Now, the problems with the models is that atmospheric chemistry and the simulation of atmospheric composition, it's very, very complicated. There's a lot that is happening. You have emissions from the surface. You also have it sort of like from lightning that actually also produces precursors to air pollution. And then they get mixed up, and then you have a lot of the chemistry. So all of this is extremely complicated. And the models are fairly sophisticated. And that also means that they are actually quite slow. And what I'm showing here, this is sort of like a schematic on what we do in the models where we discretize the different steps and then kind of like walk through them in different modules. So I don't want to go into it in detail, but really what I'm focusing on here for this work was just the chemistry. And what that essentially means is how the chemicals react with each other, because they essentially, the atmosphere is a huge dating pool for all those chemicals. And when they mix, then they convert, and then they kind of like sort of like that entire chemical system solving that is computationally extremely extremely expensive. In fact, the really more than half of the compute time in an atmospheric chemistry model is just spent on solving the chemistry, and this is shown here. So this is sort of like a timing of the computing system that we have, where you can see kind of like a model without really full chemistry. It takes, this is just relatively speaking, 100 compute times. And then once you add the full chemistry, it is 3.5 times slower. And that's mostly because of this red piece in the bar, which is the chemistry. But I also want to highlight that actually the dynamics, which is just the transport, how the components basically transport or blow around in the atmosphere, that also doubles in compute time just because you have now more chemicals that you need to blow around in your system. And just to give you some context, is for such a high resolution simulation that we just had, you need like thousands of CPUs. And even with that, you get, maybe if you're lucky, you get the throughput of 20 simulation days in 24 hours. And needless to say, you produce a lot of data. So in our sort of like real-time system that we have, we add more than 1 terabyte of per day, which for satellite people is maybe not that much, but some people are impressed by those numbers. So what I'm trying to click forward here. Let's see. Okay, so as I was interested in was, because the chemistry is so slow, can we actually accelerate it by using something like machine learning? And this is sort of like the schematic of the work that we did, again, with Matt Evans, where in the left side, this is the full model, as I showed before, with the different steps. And then what we were interested in, the chemistry, this piece here, I don't know if you see my mouse actually,
We can
but
see it.
the chemistry piece, okay, great. The chemistry is what takes 50% of the compute time. And the idea was like, can we get to something where we have like an emulator system where we still do all of the things as before, but now instead of doing the chemistry numerically, we use a machine learning system to do that. And so that could then be much, much faster. We get a speed up of like 50% if it's essentially zero compute time. So that's was kind of like the idea. Can we replace the chemistry with a machine learning system? And the approach that we took is, like, if you have machine learning, you need a lot of training data. We can produce that luckily with our model. We can generate as much training data as we want. So we ran the full numerical model, and we output essentially all of the information about what's happening in the model immediately before and after the chemistry, and that gave us the training data. So kind of like, what is the state in the model before chemistry? What is it afterwards? And that's essentially what we want to now learn with the machine learning system. And what I should mention is sort of like the full model. We run that on Discover. This is on CPU systems. It's a massive parallel system. And then what we wanted to do for the machine learning is we really wanted to do it on GPUs and on with Rapids, which is the software, but that's what we actually did on Adapt, because that was really the system to do that. So we kind of like switched between the Discover compute system for actually running the full model, do the machine learning on Adapt, and then once we had actually our machine learning system, we wanted to integrate that back into our regular system, which runs on CPUs on Discover. And I will talk about this in just a second. So this is just very briefly kind of like what the machine learning model did that we developed. So we have a bunch of inputs, which in our case, we selected 7 metrological variables and kind of like the state of chemistry, which is like what are chemical species. And then photolysis is just important for chemistry. And then we use the machine learning to now predict how do the different chemicals change because of chemistry. So essentially how much do you produce of a certain pollutant, or how much do you destroy due to chemistry? Because that's really all that the chemistry does when it does it numerically. It just gives you the tendencies of all of the chemicals. So that was kind of like the machine learning problem. And I don't need to talk about this in a lot of detail. I just wanted to put that slide on in case that you're interested. There are certain kind of like technical things that we had to step through. And I think it's kind of important to notice that I think when we started, there were kind of like still a lot of changes also to the software. And we had a couple of challenges on the way through working between the CPUs and Discover and Adapt. So NetCDF format is, well, at least at the time, was not very well supported by some of the GPU softwares. And so we had to kind of like pre-select the values and the fields that we need for the training. Then had to write them into a CSV file. Then we had to port that over to the GPU systems, and then we could actually do the machine learning. And then we had to sort of like go all the steps backwards. So it was initially, it was a bit awkward and it required quite a number of steps. But I think now the systems are much more mature and there are better softwares also to kind of like handle some of those formats. For us, that kind of like took a little bit to get sort of like the workflow going. But then once actually we had it, what I just really wanted to show is I started initially by doing some of the machine learning benchmarks on CPUs, and just to give you an idea kind of like how long it takes to do just the machine learning training on the CPUs in the regular setup where we just use the CPUs. It took 720 seconds for a particular system to learn. And then once we switched over to GPUs on Adapt, it took like 23 seconds for the same problem. And then we worked actually with the NVIDIA folks to optimize that a bit further. And then we were able to bring it down to 14 seconds. And the reason why this really mattered is that this was a relatively small case. And once we started to really scale it up, obviously, that matters a lot. And also, as always, like when you do these things, you iterate a lot of the time. So you kind of like, it's a bit of a trial and error. And so whether you wait for, let's say, 5 hours for a training or 10 seconds, it really matters in kind of like how efficient you are in moving forward. So there's no question in my mind, sort of like for this type of machine learning applications, the Adapt system was just like the absolute game changer for us. So just kind of like a few slides about the results and kind of like how we plan to apply this now. This is just to show sort of like the result where the true tendency, that's kind of like the thing that we try to predict with the machine learning. So on the x-axis here, this is the true value. And then on the y-axis, this is actually what we're now predicting using the machine learning system. And you see we're actually quite happy with that fit. I should also say what we're trying to predict with the machine learning system is just a change. As I said, how much do you produce or how much do you destroy? And then you have to add that, of course, to the actual concentration that is still in the system. And when you do that, you see you get essentially a perfect fit in this particular case. So we're quite happy with the performance of our system. And then kind of like the last bit that I do want to mention is that once we had our machine learning model, we wanted obviously to embed that back into our main model, because what we ultimately want to do is we want to run our full Earth system model with chemistry, but now we would like to use the machine learning for the chemistry instead of the numerical system. And that actually was quite difficult. And the reason for that is simply that a lot of the machine learning software is extremely good for doing an analysis, and kind of like doing fancy stuff with building your own model, but then embedding that machine learning model into some other system that may not use, let's say, Python software or so. There's just no real support for that. And so we had to kind of like dig pretty deep actually into the the algorithm that we used, which is XGBoost, and go down into actually the main sort of like C and C++ code and build our own interfaces so that we can now run it with Fortran, because all of our model code is built in Fortran. And that's something that I really didn't consider at the beginning. So I was just like, oh, once we have the machine learning model, we're just going to run it in our system. But actually, that second step of kind of like really embedded into the final system and sort of like really kind of like take advantage of the machine learning model that you have now in an operational sense, that took quite a bit of time. And that's just something that I feel now it's worth considering when you want to use some of the maybe machine learning applications, is depending on how you want to use it at the end, it may take quite a bit of time to actually be able to use it efficiently in sort of like a day-to-day application. Um, but we finally got around this, and we were able to run the model with our machine learning system. And what is shown here are the results from that. So the top is the reference model that's with the full numerical chemistry in it. And this is 1 day, 5 day, 10 days, and 30 days. This was just a 1 month simulation. And then here, the middle, this is with the machine learning, the XGBoost, and then at the bottom, there's the percentage difference. And that's just the surface concentration of ozone, what I'm showing. And you can see this is by no means perfect, and we didn't expect it to be perfect. And you see that we actually start to overpredict the ozone by like almost 100 over the remote regions. And you can see that the ozone concentrations in the original model are pretty low, then they're quite a bit higher in our model with the machine learning. So we know that this is not perfect, and we actually have some ideas in how we probably can fine tune the algorithm to make it better. But overall, we're quite happy. And we're particularly happy if we look at the surface concentrations over polluted regions, which in many cases is sort of like what we're mostly interested in, is kind of like what is the air pollution over New York or Delhi or Beijing or so. And what you can see here, the black line is the reference model. The red line is the model with the XGBoost, sort of the machine learning algorithm. And then we also had one with no chemistry, because one of the reviewers said like, well, what if you do just no chemistry, can you essentially beat persistence? And what you can obviously see is that the machine learning clearly beats persistence by a lot. And we're actually doing a pretty good job in capturing kind of like the reference model. So we're quite happy with all of this. And then finally, sort of like the model speed up that we get with this machine learning system is as we expected, essentially. So this is kind of like going back to what I showed before. In the full chemistry, relatively speaking, the chemistry takes up almost half of the time. And now, if we use the machine learning, we brought this down by quite a bit. So the overall runtime we can reduce by a factor of 2, which is nice. We would love to get it faster, but that means that we have to now tackle the dynamics of the transport. Uh, I think that's pretty much all I have here. So I for us, really, the machine learning system can help us to speed up our air quality models by a factor of 2, hopefully more. And that will enable us to do new applications, like to make better use of satellite observations and improve the short-term air quality forecasts. I think we can really do that. What we now have to do, and we have to go back to adapt and do that there, is to train on larger data sets, and then still we can optimize the coupling between the CPUs and the GPUs. I think right now we still have to sort of like manually transfer the data from Discover to the GPU systems. And that's has been kind of a bottleneck, that we weren't able to draw from the same data cloud set, so to speak, from both systems. So we had to manually transfer it back and forth. And so that's something that we have to address if we really want to scale this up. And I think that's all that I have. So if there are any questions.
Thank you so much. It's really interesting to see see your work and then also see how you've used Adapt to do it. And if you have any questions, you can feel free to write them in the chat, or you can just go ahead and shout them out. Dan Duffy says we will be getting GPOs in Discover later this year or early next year. So maybe that will help a little bit as well. If anybody has any questions for Christoph, you can go ahead and type them in or call them out. We have a question. How many people worked on this project with you?
That was Matt Evans and me, and then Matt Stroud helped me a lot on the adapt side. And then we had some folks from NVIDIA, which helped me out kind of like with the software there. So that was really nice. But kind of like from the NASA side, it was um, just me, I guess, with sort of like from the science side.
I had a question too. Maybe you
Mhm.
mentioned this, but when did you start this work and adapt? How long did it take you to kind of work through some of those issues and then kind of looks like you now have a paper out, or so how long was the
Right.
actual adapt process?
Um, so I think I don't even remember exactly when I started. I think I started more or less at the time that Matt started. Matt, correct me if I'm wrong, but I think you were pretty new then. But so maybe 2 years ago or so. But I think once Adapt was kind of like up and running, it was actually, it didn't take me that much time because I did a lot of the development on, as I said, initially on Discover, and I used Python, and that was very easily, I could port that code very, very easily onto the GPU system. So that was actually quite trivial. Um, so I think it was just for me, it was actually more also learning about the new tools that were available and everything. So it took me maybe 3 to 6 months to get everything up and running.
Very cool. We have another question. How long did it take to train the model?
Yeah, so the ultimately the full model or so, I think we were then able to train it in 6 hours once we had like everything um, kind of like going. So now if I have to retrain a model with the amount of data that we used for this case here, it takes maybe 6 hours on adapt, and it would probably take 2 weeks or so on a CPU system. Um,
6 hours with how many GPUs, Christoph?
Oh, that's just on. I did this on just one. I think I did it just on one GPU. It could be four GPUs. I'm not 100% sure if I did it actually on the four GPUs at once. I think that was one of the issues that we had with Rapids is that we couldn't fully parallelize it at that point. So I think it was just on one GPU.
Okay, thanks.
Well, great. This was really helpful. Thank you for showing us the possibilities that we can be now taking
Of course.
advantage of. Christoph, I really appreciate it. And I think we'll move into Matt Stroud's demo of the GPU cluster next. And
Okay,
then
stop
if there are other
sharing.
questions you have for Matt or for Christoph, you can ask them after Matt's presentation. And then lastly, we'll do Paul Montesano's presentation. So Matt, while you go ahead and pull your presentation up and remember to get that ball and drag it down to yourself, I'll just give a little intro on Matt. So you heard Christoph mention him. So Matt Stroud started off at CCS as an intern back in the spring of 2018, and he's stayed on and become a full-fledged employee there. And he's really helped the NCCS team and ABoVE with implementing many of the new data management workflows. And he helps us to bring all of the data over from the DAX, the NASA DAX, into the ABoVE space. And he's been a really integral part of that team. So, Matt, once you're ready, you can just go ahead and share your screen and take it away.
All right. Hello, everybody. I
I
guess
don't see
Liz
yours.
already gave me an.
Yeah. Oh,
Yeah,
there
I'm
you
trying.
go. Yep.
We're in the process of getting there. My slides aren't as nice looking as Christoph's, but it's okay.
And then if you want to go ahead and use the presenter view. Here, no, try the switch.
Can you guys see
We
the?
see we see your like the what the presenter would see. not the
Oh, that's
presentation
nice.
itself.
I don't know how to get it to not do that, to be honest.
You can try to share your desktop only.
I could do that, I
And
suppose. Let's see. Where is WebEx? Nope.
I don't know why this happens on some computers and not
All right.
others.
Maybe I'm not on a Mac. Haha. All right. We will do the desktop, I
Yeah,
guess.
and then put it in presentation view. Maybe we'll be able to see.
Does it work now?
Now try the Yeah, that
Good.
works. Yep.
Wonderful. Like I said, not nearly as nice of slides as Christoph, but it is what it is. So yeah, I'm just maybe less so much of a demo, but more of a bit of a description of what kind of resources we have on Adapt. Bit of a discussion about our new GPU cluster, how you can use it, how you can get access to it, etc. Christoph and other people far smarter than I have done a lot of good work on the GPUs, and those are more of the examples that we'll use. But I'll still show a little bit of how you can access and use it. In Adapt, as of now, we actually have two kind of GPU clusters. Christoph worked on. We'll start with hardware. Christoph worked on our legacy ML cluster, um, which specs are here: 24 by 2 CPU cores on each node, 512 gigabytes of memory for each node, and then we had two nodes with four 16 gigabyte NVIDIA V100s, and we had one node with 8 of these GPUs. And as Christoph mentioned, his workflow was able to be massively accelerated with just one, and obviously for other workloads, and depending on how development goes for Rapids, if he can scale up, it can be increasingly scaled over multiple GPUs and multiple nodes. Very recently, we got a new, much larger GPU cluster with 22 nodes, each with 20 by 2 CPU cores. So that's two CPUs, two sockets with 20 cores each, to be clear. 768 gigabytes of memory per node, and 22 nodes with four 32 gigabyte V100s each. And as Dan mentioned, moving forward, even Discover is going to have GPUs, and we're getting new systems. We're trying to increase accessibility to systems with GPU hardware, so that way many of the new softwares that leverage GPU acceleration can be used for doing interesting science like what Christoph demonstrated here. On the software side, all the systems are running CentOS 7. We have some of the NVIDIA core software installed. That's CUDA, CUDA, NCCL. We have Anaconda 3 with some curated environments with standard machine learning frameworks installed, and users can create and customize their own environments. So as Christoph mentioned, he used Rapids AI and cuDF, which are Python based packages, and he did the machine learning work through Python, which makes Anaconda a very useful tool, and you can create and customize your own environments for your own workflow as needed, as well as using the ones we already have installed. Our systems also have modules with compilers, MPI, and other miscellaneous things, which you can get to with the module tools. And we also have Jupyter Hub. Currently, we only have Jupyter Hub running on the previous GPU cluster, but we are in the process of getting one stood up to use the new GPU cluster as a backend. Gaining access. Yeah, I believe that for existing users, you guys are just a support ticket away from getting access, and you can email support@nccs.nasa.gov and ask for access. And of course, if there is anything else we need from you, we will be able to get that to you through our ticketing system. GPUs are accessible through Slurm only, so now I'll flip over to doing a demo. see if we can, back. So let me pull up a terminal. So from adapt login, SSH shell to adapt login, you can go, for the old GPUs, it would have been ML 101 or 102 for where you can submit jobs. For the new GPUs, you can go to GPU login 1, if assuming you've, or it is after you've gone to support, requested access, and been given it. If you had access to the old systems, though, you will have already been given access to the new ones. I don't know how many people in the call had access to the old ones, but for reference. So you can get to the new ones with GPU. Let's zoom out a little bit. Yeah, you can get to GPU login 1, and you can submit jobs. It's just Slurm, similar to the previous cluster of GPUs, similar to Discover, and similar to ABoVE in some ways, though there are additional parameters for using the GPUs, though we don't need to get into the technicals that much. But basically, you can submit jobs through a script. So we can go to demo, and we can write up a job script as such, and have things in it, and we can SBatch it to the cluster. It'll look like that. So using another job here, but it'll run, it'll complete, it'll spit output to a file right here. You can also have a interactive session where you do an salloc. You can test things interactively. So it says GPU login here, but actually if we do I'm actually on GPU 03, so we have 4 GPUs, 30 gigabytes of memory, etc. And you can do development testing, etc. Basically, all I have. Yeah, I don't have a ton of cool science that I'm doing because I am not doing cool science at the moment on them. But yeah, I'm happy to answer any questions that you might have about the hardware, software, getting access, etc.
Well, thanks a lot, Matt, for joining us to talk about it today. After I wanted to have Christoph show kind of those flashy highlights about how well it worked for him and how he was able to really decrease his processing time. But then I really wanted to follow up with your presentation just to show our ABoVE team how they would start to do this and just a little bit of the mechanics about it. So we had a little bit of a better sense of what we needed to do next. And I know you put a link up on your slides, and maybe you can just share that in the chat if you can. Just where people would go to learn more about it. I might be able to find it in my slides too.
Yeah. So this slide. We have some. Yeah. This is the link to our webpage for the GPUs, and you can find this on our website or follow this link. Let me open WebEx back up.
Great. I might be able to get it here. I think I've got it if you can't find WebEx right now.
Matt, can I ask a question?
Absolutely.
Great. So I was curious, what is the workload right now, or the usage on Adapt right now? Because one of the nice things when I worked on it was that there was nobody on it, so I could literally use the GPUs whenever I wanted. And I'm curious, kind of like what the workload looks like right now.
So it was on the ML nodes. It was getting quite crowded just before we implemented the new GPU cluster. And the new GPU cluster, while at this very second there are not a ton of jobs, has been running a lot of like whole node jobs for many users who we've been starting to convert over. So it's much less crowded on both, A, because we have a lot more nodes, and B, because people are moving over to the new one, which we recommend. But yeah, it's pretty easy now to get a job immediately. Christoph benefited a lot from, he was one of the first people on, and he was getting started just as I was getting started. So yeah.
All right. Any other questions for Matt or Christoph?
And I put the link in the chat, by the way.
Yes, thank you for that. And this will be posted on the website as well if you want to look back at it later. Also, I think we have others from the NCCS team online. So Mark Carroll is online, who kind of helps to head up some of this machine learning and AI work on the NCCS systems or for NCCS. So if you have other questions, there's a team online right now that could help with that too. But so feel free to ask him out or chat him in. And if I don't hear another question, we'll move on to Paul's presentation.
I will also reiterate, though I'm sure someone of a higher position could probably speak to this more, but we are trying to add in a lot more GPU enabled systems to our clusters, both in Discover, Adapt, and other clusters moving forward to make GPU accelerated science much more accessible. So
Thanks. And I see Dan Duffy has said, if anyone gets to a point where they need dedicated time on the GPU systems, please let the NCCS team know. And I see a question from Ethan that says, what other Python IDEs are supported besides Jupyter Hub, or is Jupyter Hub recommended?
well, Jupyter Hub is recommended. It's the only Python IDE that we have that I've used and that we manage for users on our systems. But you might be able to do some things with exporting when you have a interactive session on the GPUs. So I'm not entirely sure of what you can and can't do with other Python IDEs, but Jupyter Hub is definitely recommended, and we have a nice integration into our systems currently for use that we do recommend. I think you're muted, Liz.
Thanks. I had double muted myself. Thanks for that answer. And I think that if you do start to want to use this system and you're not quite sure where to go or how to get started, you can email support@nccs.nasa.gov and they can try to help work with you. Or I'm sure I'm going to put this out there. You can probably email Matt or Mark Carroll and get a little help as you get started, just to figure out where you're supposed to go and how you start to spin something up. So, or you can email me and I can put you in touch with them. And I see Dan Duffy has also said, we are focused on Jupyter Hub with integrations of Pangeo and Dask in the near future. Okay. Yeah, yes. Mark says, yes, happy to help. I love volunteering you for things, Mark. So without any other questions, I think we'll move on to Paul's presentation. And I really appreciated Paul taking his time to come and do this today as well. And so, Paul, if you want to go ahead and start pulling up your screen, I'll do my little introduction for you too.
Okay.
Dr. Paul Montesano has his PhD in geographical sciences from the University of Maryland, and he received that in 2015. But he's actually been working with SSAI, but as a contractor at Goddard in the Biospheric Sciences branch since 2006, which I didn't even realize it had been that long. And he's part of the ABoVE team. He's the lead for the Vegetation Structure Working Group, and this is an activity born out of that working group. So I'll let him go ahead and take it away.
All right, thank you, Liz. I'm assuming everybody can see my screen okay and hear me okay.
Yep.
So this talk is, okay, good, thanks. This is a quick sort of talk. My name is Paul Montesano, and this is a quick talk about primarily about the work that the Vegetation Structure Working Group has done for the ABoVE team. And so a lot of this work that I'll just be presenting here as sort of a public service announcement has been done both by myself and Matt McAnder. And Matt McAnder's on the line, and he can jump in at any point during my talk if he wants to point something out or has any information to add. But basically, I guess the background to what I'm quickly talking about here is that early on in this sort of round of ABoVE, Matt and I realized that we shared this common interest of looking at gridded Elvis data. And we also thought that a lot of other teams would be interested in the gridded version of this data. I'm talking about the Elvis campaigns that were flown in 2017 and 2019 in the ABoVE domains as part of the ABoVE project. And because this data was available, it is available on NSIDC as level 2 sort of ASCII text files. There was a pretty good opportunity for Matt and I, who sort of are working independently. We're not formally funded together, but there was a good opportunity here to kind of like come together and produce the types of geospatial or analysis ready gridded data sets that we thought would be of sort of broad interest to ABoVE scientists. And so this is a quick talk just to explain that we have gridded this Elvis LiDAR data, and we have made this data available on the ABoVE Science Cloud. So again, just a public service announcement, sort of explaining the availability of this data. So a summary of our activities, really. Elvis data is sort of a waveform LiDAR and collects vertical structure of vegetation at footprints. And we've taken the footprint level data and just gridded it and created the types of geotiff files that a lot of people are comfortable working with and analyzing. And because Matt and I both had code to do parts of this, we kind of joined forces and coded this up to be able to process the entire archive of the Elvis ABoVE 2017 and 2019 data sets sort of efficiently and store them in the ABoVE Science Cloud so that anybody on ABoVE can access them. And again, we are gridding the data that already exists as ASCII text files at NSIDC. So this is, again, we think this is an analysis ready format that most people are going to want to use when they work with this type of data. So just a really basic refresher on what this data is. These ASCII text files that are available on NSIDC sort of come as rows and columns, where each row is a specific record of a waveform, and each column represents either some sort of vertical vegetation structure metric or a terrain elevation. And so we've taken each of these columns and turned them into their own raster grid. And that's kind of what we're doing in this process, and it will sort of give people what we've done really removes a lot of front-end pre-processing work, I think, for other people across the ABoVE team who are interested in using these data. And this is just an example of what this data looks like. On the right, you can see just a color version of one of the RH metrics, the RH98, gridded at 30 meters resolution, and snapped to the ABoVE grid. So again, this Elvis LiDAR data is not small footprint LiDAR, so you're not getting the type of tree level point clouds. You're getting a coarser gridded level estimate of very detailed vertical canopy structure estimates. So where is this data? this data right now is on the ABoVE Science Cloud. And there it exists sort of as many different files. So what I'm kind of show here is like the directory organization of these data. So you can go right now after this talk if you want and find your data set of interest and use it if you're on ADAPT and you have access to the ABoVE Science Cloud. So there's a main directory right now, and if you've been using the ABoVE Science Cloud, you know where this is. So it's under pub repo. We're using the intermediate directory right now to store all this ELVIS gridded data. And there are some subdirectories in there that will be of interest to people who are going to use this data. So it's broken down by year of acquisition right now. And then within each acquisition, there's an output directory where we hold 3 important subdirectories: footprints directory, metrics directory, and metrics VRTs, which are virtual mosaics. And so my suggestion for anyone interested in looking at this data is to first go to these footprint directories and bring a shapefile. And these footprints exist as shapefiles, and so they represent the raster extents of all these gridded data. And so my suggestion is that you bring up the shapefile or the KML, bring it into whatever program you're working in, and kind of examine the spatial extents of the data to find your specific data set of interest, at which point you can kind of grab that. And the reason why I suggest that is because while these data are arranged by flight line name, in the metrics directory, there are a few different resolutions. And within those resolution subdirectories, there are tens of thousands of files. And so if you sort of just go in there and do an ls and start poking around, you may regret it. So it would be good to kind of know what you're looking for, I think, before you go poking around in the subdirectories. And if any of this is unclear, I can clarify this stuff. I'm going to be writing, or we're going to be writing, some just basic metadata to store at the top level in the code directory, which may or may not be there at this point. And then all the code, the R code and the bash shell scripts that we've used to crank these data out will be made available soon, as soon as they're cleaned up. So just a quick explanation of these footprint data, which is a form of metadata, which will help you kind of explore where the data is. So we're providing these data right now at a couple different spatial resolutions. I think we have 15-meter grid sizes and 30-meter grid sizes. There also may be a 20-meter grid size, though I'm not sure if that's complete yet. But as you can see from these spatial footprints, you may be thinking, why wouldn't you just grid at the finest resolution possible? And so you can see from the spatial footprint that the reason why you might not want to go down to the 10-meter grid cell resolution, which is sort of consistent with the 10-meter diameter footprint of the ELVIS waveform, it's because you'll get a lot of no data area. And so you can see in that little zoom in of this shapefile footprint that when you grid at a finer resolution, you get some no data along the edges of the scans where there wasn't enough overlap to fill in and create a spatially continuous raster data set. Whereas in the 30-meter footprint on the right, you can see that same no data issue is not existing because you're gridding at a coarser resolution. So what data are we talking about? There are 31 grids, 31 metrics for each individual flight line. So again, these are consistent with the information that's already in the ELVIS level 2 ASCII text files up on NSIDC. So there are, for the most part, there are 23 relative height metrics describing vertical vegetation structure. There's one complexity metric. There's a ground elevation data set. And then there's also a footprint count. So there's a per pixel count of each of how many waveforms went into the mean estimate for each grid cell. And then there are 5 canopy cover proxies, and this is a very rough estimate of tree canopy cover at various vertical thresholds. So we have 5 of those right now, and so we have canopy cover estimated for canopies above 1 meter, above 1.37 meters, above 1.5, above 2, and above 5 meters. So there's a number of canopy cover estimates, and we'll explain in the documentation how those were made. Those are available for people as well. And there's also a canopy complexity estimate, which again is already in the level 2 data set. So just to end here, the code is right now is in a private repository and it's getting cleaned up. We will make that available in the ABoVE Science Cloud top level Elvis directory. And we'll also open up, I think, the GitHub repository here. So there's, the data is there. The documentation is not kind of complete yet. A lot of work has gone into getting us to where we are. Matt McAnder has done a lot of heavy lifting. You can see here again the adapt location where you can find this data if you're interested in. But feel free to kind of ask us any questions if there's anything that needs clarification. So thanks a lot. This is kind of our contribution to the broader ABoVE team, and we hope it's useful. We did it because we think it will be useful. So we hope people can use this data. Thank you.
Thanks, Paul and Matt McAnder for that for this presentation. And we've gotten a couple questions that have come in. One of them is, are these gridded products only available in ADAPT? And I think the answer to that is that right now, yes, they are. But I know we had talked about maybe seeing if this is right to put at the, at the ORNL DAC as well. And I see Yashing is on the line here too from the ORNL DAC. So I'm glad you got to hear this.
I think at some point we might. I guess Matt and I will talk and see how to make that happen and when that makes sense to make it happen. So I'd be happy
I think it's a good idea to talk about that. I think people would be very interested in having it via the DAC as well as on ADAPT. What sort of do you get a file size reduction by the fact that you're combining? There may be multiple Elvis records in each of the gridded cells.
So I should point out that each individual flight line, our RH metric TIFF is very small, maybe about 250K. So individually, these data are not big. But I guess collectively, if you were to stack them up and then kind of try to display across broad extents, like you see here in the background, that could be cumbersome. So we have the virtual mosaics kind of to do that yet. However, those are a little funky sometimes, and at least in QGIS. Matt and I also play with these data in Google Earth Engine, but that's a different story. Individually, these data are not too big.
Mm-hmm.
Hi, Paul. This is Yashing from Oak Ridge. I totally agree with Liz and Peter, and this can be a very good product that the ORNL DAC is willing to take. So ORNL DAC is also the selected data repository for the JEDI level 3 and level 4 products. So very similar to the graded Elvis data products that you produced. So let's have a conversation on this to see if it's appropriate or what's the approach to get the data in if we want to do it.
Yeah, thanks. I know Matt has was definitely interested in that. I think we just have to figure out how to get that done. We might need some help. He and I have been kind of working on this primarily, and so it would be good to kind of enlist the help of some other team members maybe to do some of that stuff as well.
Yeah, I think we could certainly help to get some of that taken care of. And you have put so much work into the product and the metadata already that I think the DAC can help too in finalizing some of it. So I think we should keep exploring that. Yashing, you also had a question that you had typed into the chat. Do you want to just go ahead and ask it since you know how to unmute yourself?
Oh, sure. So my question is just about some more detailed information of how your regrading process. So I'm wondering if your regrading codes written in R and Bash, as you just mentioned, can be easily adapted, say for a different target spatial resolution, or if users want different resolution from 30 meter or 50 meter.
Yeah, and Matt can add some stuff too, but yeah, Matt wrote initially the code, and it's really kind of straightforward to reprocess at a different resolution, and that's what we've done. We have 15 meters and 30 meters and maybe 20 meters as well. And the reason why we were able to run it kind of so efficiently is we used many, so we didn't use like GPU processing. We used just many VMs with many CPUs on Adapt. And so we can process the entire 2019 archive in, I don't know, an hour or so. So it can be done efficiently. Right, Matt?
Yes, and right now it is simple averaging, and there is some, certainly a more nuanced approach can be taken. It just it seems that the centers that fall into the pixel count for that pixel, so it's not even spreading it over multiple pixels at this point.
Oh, I see. Thanks, Matt. You actually addressed my second question. A similar question just came to my mind was, I know that JEDI data, the equipment on the International Space Station collected very similar canopy structure data. At a slightly coarser footprint level, it's a 25 meter footprint size. They also produce graded products from the 25 meter footprints at the global scale. So I'm wondering if you've had some conversation with the JEDI team to check what kind of regrading process they have been using. I mean, ideally, I think one consistent methodology applied in both JEDI and obvious data for canopy structure information can be helpful, especially if users want to combine different data sources together.
Yeah, I do work with some members of the JEDI science team, Laura Duncanson and John Armston. So there's been a little bit of conversation about this here work. So I guess the quick answer is we can change the way that we do this gridding, or anybody can change the way that this gridding is done, because like I said, you'll have access to the code, and that code can be sort of adapted to specific needs. I don't have any plans right now to kind of redo it in any specific way, but if there's something that's important, I can talk to John and Matt, and I can, I guess, talk to John Armston and see what we may have missed and see what we can do better. If that's what you mean. So there is some back and forth, in other words.
Right. Yeah, I did see John Armston's name on the previous presentation. So glad you have the connection with the JEDI science team. I think they are still finalizing their grading algorithm for the level 3 and level 4 products right now. So yeah, I think having some conversation will be very helpful.
Okay.
Yeah,
And also I should point out, oh,
I was just saying, I was talking to Scott Get and Richard Massey about some recent work that they're actually running the Jedi canopy cover algorithm on some of the Elvis data. So I haven't, you know, that has started. I don't know how much it's going to be, but I'm going to follow up on that.
yeah, Matt, and that's a good point because apparently John and the Jedi Science team, they have pretty sophisticated footprint level algorithms for calculating canopy cover, and I think, is it leaf area index? I can't remember, or plant area index, that would be an improvement to sort of the quick and dirty representation of canopy cover that we have here. And so at one point we had some designs to add those approaches to sort of the waveform, so basically to enrich this data set a little further with using their algorithms. We haven't done that yet. There might be a lot more work in that than I recognized at first, but it's been discussed.
Great, thanks.
Thanks everybody for this great discussion, and we've reached the hour, so we'll go ahead and end to respect everybody's time. If you have additional questions, you can feel free to reach out to me and I can put you in touch with our speakers, or you can reach out to our speakers directly. And if you have questions about your NCCS account, you can always feel free to email support@nccs.nasa.gov. I really appreciate all three of our speakers carving out time to talk today, and Matt McKinder as well for carving out time to talk today. It's difficult in this day and age to fit everything in, and I appreciate everybody's work. And we'll see when we schedule the next one. If any of you online have a talk that you want to give to tell about how you're using the ABoVE Science Cloud for your research, please reach out to me. I'm always happy to work with you and set something up. So thanks again, everybody, and I'll talk to you all soon.
Thank you.
Thanks. Bye-bye.
Bye.
Bye.